course, I forgot all my markers, and of course, I don't have any up here. Jesus. H Christ. What? That's a pin. That's not a marker. Maybe this one actually works. No. It's been that kind of day. I'll be right back. Start. What we need to talk about today is good old Archimedes principle, and that'll be the last thing before the test. Is the last object or item for the test. Last thing we need to know. We're not going to do anything on Bernoulli, even though I brought some Bernoulli stuff in that we're going to play with here in a second. So let's just take a look at the good old Archimedes principle and the buoyant force, and then we'll look at some of the Bernoulli things. We'll blow up some pop can. We'll blow up a pop can with a ping-pong ball here, and then we'll talk about the test. Okay, and which will be Tuesday, and we'll be fine. We'll be fine. Trust me, it'll be okay. Except for the video course people, because they haven't gotten any of the videos yet. So, what's that? I would prefer it, but the Tuesday after Thanksgiving. What?
No, that makes sense.
What?
We should do ours next Tuesday too. Or
What?
Thursday.
Next Tuesday or Thursday? No, I don't want to do it Thursday.
Tuesday after, how about Tuesday? I mean, like after Thanksgiving.
No. We'll do it Tuesday. Everything's fine. All right. Yeah. If I hadn't sent it to, I kind of screwed up on it. You all have been blind. You wouldn't have known anyway. So, all right. So just pretend like you still don't know. All right. Now, which is impossible. All right. Let's talk about the buoyant force. Basically, and then we'll do a problem from it. Basically, here's the buoyant force. It's the change in pressure on something. It's basically equal to this. All right. Here's what I got. I've got a block in water. Okay. Now it's displacing some water here. This wooden block that's floating there. Part of it's under the surface, and that part that's under the surface has displaced some water. Okay. And the force that's keeping this up, right here is the buoyant force. Of course, we got mg trying to pull it down. And we've got, that's about it. All right. And so, what two forces do I have here? mg and the buoyant force, right? So the buoyant force is equal to the buoyant force, when everything's in equilibrium here, the buoyant force is equal to, well, since this is equal to 0, FB minus mg equals 0. So the buoyant force equals mg. Kind of, sort of, maybe, a little bit. But there's something, so it's pushing up, and that's probably a bad derivation of that thing. Let me go through that one more time. Oh, yeah, it does. Equals mg of the fluid. That's what we got to do. We got to look at this mg of the fluid. That's it. So the buoyant force actually equals this. Equals rho of the fluid times its volume times g. Because rho times, that's the main thing that we're after right there. Rho times the fluid is equal to the volume times g. There we go. There we go. And in other words, Archimedes' principle says this. The buoyancy force is equal to the weight of the water displaced. Okay? It's equal to the weight of the water displaced. Now, if this item, what's the rho of, what's the density of water? Okay, you chemists. No more chemistry answers. It's a physics answer. Oh, that's the chemistry answer. No, I don't want the chemistry answer. I don't understand chemistry. I don't get it. What? 1,000, right, 1,000 kilograms per meters cubed. per cubic meter. This thing's about a cubic meter. And so if this thing was an aquarium completely full of water, it'd weigh almost a ton. Okay? Water's heavy. It's very heavy. All right? And, all right, so that's that. Now, let's say we've got a human body. And let's say its density is equal to 980 kilograms per meters cubed. Is that thing going to float? Will that body float? Sure it will. Why? It's less dense than water. If it's more dense than water, it's going to sink. Okay? Because the buoyant force isn't strong enough to keep it in equilibrium. And it'll actually accelerate downward. And in fact, that's where, in fairness to good old Aristotle, when he was saying that a heavier object will fall faster than a lighter object, he was actually doing a thought puzzle of equating air to the same thing as water. Okay? And because if you take a big heavy rock, it's going to fall a lot faster than a light pebble in water, right? When you drop them, it should. And so that's what he was, I think it should, shouldn't it? Yeah. Oh. What's that?
It's a law.
Yeah. And but in air, but in a vacuum, which is not water, that won't be the case. And so, in fairness to not Archimedes but Aristotle, people followed Aristotle's thought process from minus 400 AD up until about 13 or 1400 AD. So he held sway for quite a while, but finally the Age of Reason came about, which caused other problems, but that's all right. Nuclear weapons. But anyway, so there we go. So that's in a nutshell the buoyant force. Now, basically what I'm going to ask you on a test having to do with the buoyant force will be something like, we'll do a problem that's real similar to it. It'll be nothing too tricky, but it'll basically be something like this. It'll say, like how much force does it take to push a beach ball underwater? Have y'all ever tried to do that when you're in a swimming pool? Take an inflated beach ball, you try to push it out. It's hard. It's hard to do. In fact, it helps you float. Why does it help you float if you hang on to it? Because it's to displace that entire beach ball, and I've got one in this. I'm going to bring it out here in a minute, but I'm not going to displace it in water. But anyway, basically what you're trying to do is you're pushing against a force that is equal, and the more that water that it tries to displace, the harder it gets to push down, right? Okay, until it's completely submerged, and then when it's completely submerged, basically what you're doing is you're pushing that weight of water, of that volume. Okay, the weight of water caused by that volume is what you're pushing against. So that's why it's so hard to get like a beach ball under the water, because that air doesn't want to go there. All right, so it's a lot of, and it's not heavy enough. The air is not dense enough so it'll float, because it's real easy to push a bowling ball underwater. You just drop it. Ooh, there it goes. Okay? But to get a beach ball, because its density, by the way, the density of air is equal to 1.29 kilograms per meters cubed. Okay? So what you're trying to do is you're trying to get buoyant force is going to be the volume of that beach ball times 1,000 times g. And so that's a pretty strong force that you're trying to counteract. Yes?
Does the volume of the water, does that affect the difficulty or the amount of force that's needed to submerge small?
No.
So you could have a small container and it would be the same amount of force?
Okay. James is asking the $1 million question where we talk about static fluids. All right? And the $1 million question is, does volume have anything to do with the pressure, or what is it? Has everything to do with pressure. It's the height. It's the height. It makes no difference what the volume is. All right. And that's why, because if volume had a problem, then the Panama Canal wouldn't work. Because you have those big ships coming in, So it all depends on the height. Okay, is the way buoyant pressures and all those kinds of things work. Now, of course, if you got a small, little, thin, little puddle, that's not very deep, you're not going to get, not much is going to happen. All right. But anyway, so you might have a question like, you've got a 20-kilogram girl sitting on top of a beach ball of such a radius. Okay. Is she providing enough? How much of the beach ball is submerged, neglecting the weight of the air inside the beach ball, for the most part? Because it will have some air. So what you would do is you'd go, okay, she's sitting on top of it, so she's got a G pushing down, and the buoyant force actually, the entire buoyant force is pretty much up for a beach ball. So how much is she emerging under the thing? Let's take a look at that, because it made no sense what I just said. All right. So you got a little girl. Let's say she's 30 kilograms. That'd be about right. Well, she's about 5th grader then, or so. All right, so you got this little girl. She's sitting on this beach ball. Big beach ball. Anyway, she's much bigger than this. This is drawing from her knees down. Okay, there's her toes. Well, that's kind of creepy. All right. Forget that. Let's just turn her into our proverbial block. All right. There she is, all 70 kilograms of her. We've just turned her into our block. Okay. All right. Now then. How much? So she's pushing down with a force. Okay. She's pushing down with a force, and that's about how much. And so we want to know how much of the beach ball she's actually submerging. Okay, how much of that beach ball is she actually submerging? So what's the force that she's pushing down with? mg. Forces. Some of the forces in y direction is equal to mg minus. There's a buoyant force pushing back up. Okay, buoyant force pushing back up. All right. Well, that's stupid. Let me do this. Gosh. Thank you. Thank you for not pointing it out. Oh, come on in. Come on in. All right. Now, I wasn't really pausing to wait on you. I'm having a bad night, so things aren't good. You probably would have been better off just staying home. All right, here we go. So the buoyant force then is equal to mg. Oh, okay. Well, then that's because I'm neglecting the weight of the ball and the weight of the air in the ball. Okay, because compared 70 kilo compared to a beach ball, it doesn't add that much to the problem. All right. So going well. This is how much water is displaced. Okay, so the volume, so rho, so F of B equals rho times the water times the volume times G. Well, I know everything. I know mg. So M equals rho of the water times the volume. So the amount of volume is M over rho. That's the amount of volume that's being that she can displace there. That's kind of a cool little relationship. I just kind of discovered. Okay, so that's the volume. Now, what's the overall volume of the beach ball if you know the radius? How do you find the volume of a sphere? No, times 4/3 pi r cubed. I was getting ready to say no. Integrate that thing, but basically integrate that thing and multiply by 4, and you've got the pi r squared is the area of a circle. Pi r cubed gives me the volume of a sphere. So you'd figure out this volume right here, and you would take this volume right here. Let's say this is volume 1. So the percentage submerged would be volume 1 divided by 4/3 pi r cubed if r is given. Okay? So I think I think I'll give that question now. I didn't explain this to the matinee class. Yes.
How come it's not mg over there? It's just m. What happened to the gravity for FP?
Oh, you're so picky. Okay, this guy? There you go. That's fine. That's a good question, though. It's a good question because, you know, otherwise we're just doing magic, which is Kansas science standards. We don't do that. Sorry. All right. Anyway. Okay. All right. Now,
Do we have to multiply that by 100 to get the percentage? Or do we just keep the percentage?
oh, yeah, then you have to multiply by 100 to get the percentage, yeah.
So in the test,
I'm so used to getting a decimal and just going, oh, okay, and sliding over to.
if put the decimal in the test and it'll be wrong, right?
No, because I'm grading it.
Okay.
It'll be fine.
All right.
So why are we getting a percent?
What's that? We're getting the percentage. Find the percentage of the ball that's submerged. Okay.
How does that translate to height?
What? It doesn't. So that's. It doesn't.
We're finding the percentage of diameter.
Yeah. It has everything to do with the volume. All right, because we're dealing with weights here and forces. Type thing. All right. Now, when we get to pressure, though, now let's take a look at problem 32. That was one of the problems I assigned from chapter 9. It's kind of a curious little problem, and I actually had issues with it. I had trouble with it. So I figured if I had trouble with it, I had to go ask, why did I get this wrong, or what was I thinking wrong? And then I figured it out. I went, oh, this is what I did. I double added for the pressure. Now remember, with Archimedes' principle, in fact, bear with me. I'm going to take about 2 minutes of your life here that you won't get back, and you're going to watch me blow up this thing. You can't be a smoker and teach physics because you're always blowing up balloons or beach balls. Actually, you can't be a smoker. I'm a reformed smoker. The biggest kind of anti-smoking Nazi. Are you getting all this tingy? All right. Whew. There we go. All right. Now, this next problem, what was I going to do with that? Oh, sounds like I have no idea. I don't even know why I came. But, all right. Okay, and I don't blame her. All right. Okay. Oh, we're going to do a Bernoulli thing with that here in a minute. All right. Now, let's look at problem 32, which I assigned to you all. Because here's, oh, that's right. I was going to use this for the Archimedes principle. Gosh, dang. Get your act together. Okay, now, this has a certain amount of pressure, okay? If I put like a little pressure gauge, if I could figure out a way to put a pressure gauge on the side, go get some kind of pressure, that would give me, actually what the gauge would give me would be the difference in pressure, because there's pressure, there's air pressure. Remember, all those little air molecules are bombarding this thing all over the place and causing that 1 atmosphere or 760 torr or 1.01 times 10 to the 5th pascals of pressure all over the outside. So when you do your tire gauge and it says 32 psi, it's actually more at 47 psi is actually the pressure that your tire is feeling, because it's got the pressure on the walls pushing out, it's got the pressure pushing in, so you add the two together, and there you go. All right, so we're going to take the difference in pressure. So when I squeeze this thing in certain places, see, it's equal throughout. Okay, however much pressure I put, in other words, the pressure is distributed evenly throughout the area. All right, so here's the thing on problem 32. Okay, which says this: got a barrel. All right, got this barrel full of water. Okay, and it's got a lid, and the area of the lid of that barrel is equal to 0.2 meters squared. Okay, and then out of that barrel, and we filled it completely to the brim with water. Okay, filled it completely to the brim with water, and then we've got this like thin piping coming out of here that goes up 12 meters, and it's got the area, cross-sectional area of the pipe is equal to 5.0 times 10 to the negative fifth meters squared. So that's pretty small little pipe there. Okay? Now then, what we're going to do is we're going to fill this thing up with water, and once we get to 12 meters, bang, the barrel explodes. Okay? The barrel explodes. Now, that seems kind of weird to us. All right? Because we're only going to put about, this is getting to the height thing that James was asking about earlier. We're only going to put a little bit of force in here. So let's take a look. Your question asks this. Part A of the question is, how much does this column of water weigh once I get it up to 12 meters? How much does that column of water weigh? How do you figure that out? Weight is what? Yeah, by the volume times the density times G. Okay? So the weight of the water is equal to rho V times G. Okay? Where rho is 1,000 again, times 5.0 times 10 to the negative fifth times the height of 12 meters. Because area times height equals volume. Okay? Times 9.8. And because this 10 to the fifth is so darn small, this only equals like 5.88 newtons. Hardly nothing. That's like 6 tennis balls. Now, if I just went up and put 6 tennis balls evenly over that lid of that thing that's full of water, it's not going to explode at all. But with that pipe that's up there 12 meters high, I'm creating a tremendous amount of pressure. Tremendous amount of pressure, and that pressure is equalized throughout the thing, so it blows the lid off. Okay? And they want to know, well, what is the pressure? What's the pressure caused? What's the change in pressure caused by this pipe? Now, right now, there's this equal amounts of air pressure everywhere. You know, P naught. There's before we fill it up, there's this P naught everywhere, and there's P naught there, and so there's a counter P naught here. And so what we're going to do is when we do that, we're going to look at the change in pressure. Because right now, it's feeling that pressure that's coming down there now, but we're going to add that change in pressure to this thing, and so we get this. So it wants to know, what's the pressure caused by the pipe? Well, the pressure caused by this pipe is rho GH. Aha! So we're taking out this little volume guy. And the pressure is pretty intense. It's pretty high. Because we're taking out this 10 to the negative fifth thing. Because I don't care how wide it is. I'm just worried about how tall it is. Okay? And so I've got 1,000 times 12 times 9.8. Which is about, boy, I wish we had a better system. I wish gravity was 10. Then life would be so much easier. But anyway, it's not. So this is like 10,000 times 12. It's about 120,000 or 118. Let's call it 118,000. And what's my units for this? Let's call it roughly 118,000 what? What's that? Pascals. Yep, pascals. 118,000 pascals. And then it wanted to know, what's this change in pressure on the lid? What's the change in pressure on the lid? I go, I don't know. Let me figure it out. So here we go. We can do it this. So we'll do this. So what's the force on the lid then? This force that's pushing up here. There's a force pushing up there that's counteracting that. That's, boom, blows the lid off. Well, that force, well, the pressure is equal to force over the area. So we got the pressure here. So we take that 118,000 equals some F over the 0.2 meters squared. You take that 118,000, multiply it by 0.2. You get about I don't know, a lot of newtons, about 3,600, something like that. I don't know. It's quite a few. When you multiply this out, basically, if I multiply by 0.1, I'm going to get 118.00. It comes out to be what?
23,600.
Yeah, because then if I add this to it, yeah, I get 23,600 newtons. Now, what we've done is we've put 23,000 tennis balls on that thing, and that made it blow up. Or tried to stuff 23,600 tennis balls inside there. Of course it's going to blow up. That's a lot of force popping up there. Okay. All right, so we know a little bit about Bernoulli. You don't know anything about Bernoulli yet. We're going to talk about Bernoulli's right now. All right, here's the deal. Quiz question, quiz time. Which has more pressure, fast-moving air or slow-moving air? Which has more pressure, fast-moving or slow-moving air? They're the same? Fast, slow. Let's get on with it. It's 6:07. We want to get out of here. Tell us about the quiz so we can go, or test so we can go home. All right. I'll tell you. There's force of nature here. All right? And here's another force of nature. You're watering the yard. And your little brother comes by, or sister. What do? Exactly. That's a force of nature that you can't, that should be in all the physics books. Force of nature, little brother or sister comes walking by and you're with a hose, you squirt them. Can't help it. How do you do that? You point it at them and do what? Yeah, you got to put your finger over, or your thumb over half of it or so, or a little bit. Now, the fast-moving water is shooting out here, and the slow-moving water is behind your thumb. Where's the pressure? In front of or behind your thumb? Behind. So where's the slow water? Behind. So in fact, it's that pressure difference that gives us the force, P over A, this pressure times the area gives us that force that accelerates those water molecules to make them go faster. All right? It's the pressure difference between the two. Okay? So, Mother Nature does not like to have pressure differences. Okay? So she rushes in to fill them. Okay. Here's what we're going to do. Have you seen this before, James? All right. Well, anyway, first of all, we're going to have a competition. James is kind of a big, burly guy. I'm kind of a small, wimpy guy. Amanda, hold that in for James. James, here, you're going to race me. Because I know and Kendall, could you hold that for me? Just hold that in. Make sure there's no air gets out. All right. So, James, you might have to stand up. Okay, now what we're going to do, have you ever seen this before? We've never met. No, I sound like one of those magicians. All right, but anyway. All right. Now what we're going to do is we're going to race blowing this thing up. We're going to blow up this balloon. Are you ready? 1, 2, 3, go. Oh, hold it tighter at the end. Okay, try again. Oh, keep going, James. There we go. Much better. Much, much better. All right, now let's try it. Now, what was the difference? All right, thank you, James, for millions are going to watch you now on closed circuit television. We're on right after Wayne's World. All right, party time, excellent. But anyway, what was the difference between the way I was blowing it up and the way James was blowing it up? His mouth was covering the thing, all right? And so when I'm back here and I got the fast-moving air coming out of my mouth, Mother Nature doesn't like that, so she rushes in. She helps me out. She sends extra air in there to equalize the pressure, try and equalize the pressure. He was blocking that from happening. All right? It's kind of like this fall, I was coming down from God's country to get down here. I hadn't quite crossed the moat yet of the Paseo Bridge. Well, I don't go to the Paseo Bridge anymore because it's kind of messed up. But there was some guy with his pickup truck full of leaves, and he didn't have a cover on it. okay? And he's driving along, and the leaves were doing a curious thing. They were kind of floating up and getting above the cab of the truck and then blowing back this way, you know, once they got the force of the wind. Blowing, now it's going, the guy has to be from Excelsior. But actually, I'm the one with the 15 bags of trash, so he was actually probably smarter than I was. But anyway, what was going on? But the leaves were kind of floating up like this. Well, what was going on? You had the fast-moving air going across the top of the leaves, okay? And you have the regular pressure underneath them. It's much less pressure up here, and so you got this higher pressure pushing up, floating the leaves up until they get caught by this the air force that's flying up over the top of the bed of the truck, or cab of the truck, and then they were shooting off in the other direction. Now, so this Bernoulli force is pretty strong. All right, this is the Bernoulli force thing, and this is basically a leaf blower that the guy from Kearney didn't have, or Excelsior in the truck, or maybe he did blow them all. So we're going to turn that on, and then it'll stay right there. It should staying pretty good, and it's actually a pretty strong little force because you can kind of go like this. You can move it back like this. Are you getting all this? All right. This is for posterity now. All right. There we go. Emmy, I can smell it. All right. All right, now. So air pressure is pretty strong. Now we're going to really see how strong it is. This is a good thing. All right. This takes me about 3 minutes to set up, or 4. So I apologize for that. But we'll talk about the test that Mr. Courtwright does not want to take yet, but we're going to anyway. Full speed ahead. What am I doing? Oh, yeah. Here we go. All right. We've filmed this before, haven't we? Okay. Yes. I love this thing. Let's see. Go back a little bit. All right. Now, what I have to do, first thing I have to do is I have to get a really tight seal. First thing we got to do is make sure we put a ping-pong ball in there. Okay, what's the pressure that's banging around per square inch here? How many pounds per square inch are banging around the room? About 15, 14.7, 15, right? And so that ping-pong ball is about a square inch of thing. So all of a sudden, 15 pounds of pressure are going to smack into him. Because what we're going to do here, have I done this one for you all? Oh, okay, good. All right. What we're going to do is we're going to cut. The most important thing about this whole experiment is you don't lose the start of the tape. All of you, any of you who have moved yourself before know that you do not lose the start of the tape. Otherwise, you got to go back to your wife and say, can you move the start again? All right.
Are you going to create a vacuum with that?
Oh, boy! James is on it. He's all over it. Ooh. Careful. Easy now. Remain calm. Kevin Bacon, Animal House. All right. Yes, we're going to create one heck of a vacuum because I seal this really, really tight. Tight, 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 tight seal. Yep. You got to get the really wide one though. If you use normal ones, because remember, I hope I don't have to use. Well, I'm going to use my line right now anyway. Remember, to tell the difference between the three main sciences. If it's goopy, it's biology. If it stinks, it's chemistry. If it doesn't work, it's physics. So, I hope this works. Oh, but then it just falls into the realm of physics. All right. So we're going to put this right here. Yeah. Got a good seal, I think, this time. And I did remember to put the ping pong ball in there, I do believe. All right. I'll probably have to ask Robin and Steve and Michaela and Don. Yes. I used to be, about once a year when you were a young lieutenant in the Marine Corps, you had to be the range safety officer, and you have to go to the rifle range about once a month while the Marines are out there qualifying. Make sure no one was downrange. One time we were there in Quantico at, well, it was actually when I was a lieutenant, I was actually firing on the range. We had some deer hunter come walk up over the berm from where we were shooting, right over the targets, where the targets were. It's like, ugh! Do you realize that there are 50 lieutenants now with their M16s pointed at you, loaded? Luckily, they're second lieutenants and they can't hit anything. But, all right, now then. Put the Coke Zero here. Oh, I got to plug it in too. All right, now we're going to back this thing up. I kind of like the way that thing. Look at that. Okay. And then we'll put the little Coke can right here. Yes. Still too high? There we go. There. All right. Okay. Make sure we turn this on. Oh, we got to plug it in. See, if I'd had my act together, I'd have had this all set up, or I'd have had one of the TAs set this all up ahead of time. I got to make sure this isn't pointing down range. Okay. Here we go. Now we're going to suck all the air out of it. Got a vacuum here. It's going to suck all the air out of this thing. Here's my firing pin. Okay, got my firing pin. I'm going to poke a hole, whoo, and that little bitty hole, and we're going to have 15 pounds per square inch come rushing in there at the speed of sound, and at the speed, close to the speed of sound, this ping pong ball is going to come shooting out of here. Here we go. We gotta wait for it to kind of stop popping. All right. All right, let's see if it works. Here we go. Oh. Oh, it worked. Where'd the ping pong ball go? Oh, it forgot to come out, but that's what. Oh yeah, no, it's in there. It's in the can. That's the best it's ever worked. All right, that one was too fetty. I like that one. All right, but anyway, that's physics at work and play. You were not expecting that big. Oh. When we had, you should have seen when we had the kids from Woodland Elementary and I did it. Oh my gosh, they hit the deck. Like, oh, drive by. But it's actually from poor babies, but anyway. All right. Hey, that worked. That worked. Okay, now let's talk about the exam. Now, see, if I ran the world, that's the way we'd have physics class. No, but we'd only have like 12 of you in class, and we'd just build things like this, and you'd calculate the stuff. And you'd probably learn more physics than you'd possibly, but we wait till grad school to do that with y'all, so because we're strictly into volume here, all right? Okay, so anyway, well, that was pretty cool. That worked. All right, now, so you see how strong air pressure, wow, that's the best one we've had yet. Cool. All right, now, what's going to be on the test? A lot of Chapter 7 stuff, and let's talk about it real quick. Take about 15 minutes, we'll go through what's all going to be on the test. Nothing on Bernoulli on the test, but basically Bernoulli is, again, the whole reason you take science classes, unless you're trying to get into some like big highfalutin follow-on school or graduate program or something, if you're just a regular Joe just getting his college degree, the whole reason you take science class is so you can be a better parent. All right. In other words, when your kids ask you why is that, you can answer them. All right. And so why is the barometer falling when the weather gets bad? Because lower pressure. Mother Nature doesn't like that, so she rushes in energy, into the thing. And actually, there was that low pressure, very low pressure that happened in the wake of Katrina that caused all the problems. Remember when the storm first went over, they were like, oh, they averted disaster. Then all of a sudden, disaster struck because the storm surge caused the pressure was so low that over Lake Pontchartrain and over the Gulf there that the water rose up many, many feet, and then it broke and then the pressure, because it got higher, the pressure on those Corps of Engineer dikes broke. All right, but also, I mean, any kid who's had a bowl of cereal and has put it in the sink, because Mom said put it in the sink, can tell you, if sea level is here, you don't build your city here. All right? Because what's going to happen? As soon as the water starts to spill in, just like you all done that with a bowl in a sink, you just kind of tip that's basically what happened. The bowl got tipped and water rushed in, boom, sunk New Orleans, or the Ninth Ward mainly, stuff like that. Okay, but anyway, so that's all right. No more political comments in physics class. Okay, but that's actually what happened. It wasn't the hurricane so much; it was the storm surge afterwards. And all the rock jocks, the geoscientists, will be able to tell you all that kind of stuff. Okay, now, so let's talk about what's going to be on the test. I've said that 18 times. Let's talk about it. Oh, okay. If you were given, how do you find S, the arc length of something? All right, see, you're ready for the test. All right, so you're off and running. Okay, R times theta gives you the arc length. What if you're given the arc length and the amount of time it takes for something once it was spinning to come to a stop? Do you think you could find the average angular speed? What's the average angular speed equal? You know this guy? Theta equals omega. Ooh, what's him? Angular speed times t. So if you find theta and you're given t, do you think you can find omega bar? Looks like freshman algebra to me. All right, got it. All right, and should we go to? Okay. Since y'all had so much fun with it on the homework. I know Greg did. The pilot, okay? Remember the pilot? I'm going to throw another pilot question at you. But it'll be okay. But it'll be all right. The pilot, when he's going in his vertical loop, oh yeah, Rashonda's eyes just rolled back in her head like she is going in the vertical loop. But anyway, this time I'm going to give you the acceleration. Ooh, but it's going to be given to you in G's. If you're given the acceleration and you're given the speed, do you think you can figure out the radius? Should be able to, right? All right. Yeah. Remember, pilots can't pull more than 4 Gs, otherwise they pass out. All right. So even with G suits on. Okay. Angular acceleration problems. In other words, on your cheat sheet, make sure you bring in this. All these little guys that make our life so much fun and simpler. Those guys, and know what they mean and how to apply them. And also keeping in mind that R omega AC equals R omega squared. AC equals V squared over R. Those guys. And know what they mean. And know how to use them if you're given a certain problem that asks for a bunch of them. Oh, and we had so much fun too. See, I picked the greatest. Whatever problems I get the most emails on in frustration, those are the ones I picked for the exam. So, stop sending me emails. All right, no, I'm kidding. But anyway, let's see. You all really enjoyed, most people really enjoyed how high up you would be, what's your gravitational pull. Okay? But this time you might be on the moon. So what would you need from me if you're going to figure out what's the gravitational pull if you're so many kilometers in the air from the moon? Like say you're in Apollo, you're in the little Apollo module and the eagle is landed down below. And you're circling, what's the gravitational pull that you feel from the moon? What would that be? What would you need from me? The moon's gravity? The moon's what? We need the moon's, not the moon's gravity, but the moon's, no. Moon's radius? There you go. What else? Mass. In other words, F equals G M1 M2 over R squared, except this time M1, or the acceleration, is going to be G M of the moon over R squared. That's why you need the mass of the moon and the R squared. However, what if you're certain up? Remember, you got to add that R plus H squared, and you got to find H maybe, or something like that. Okay? Okay, chapter 8 is going to be one problem or 20 points. Okay, and chapter 9 will be two problems. So far, we've done 10, 20, 30, 40. No, there's be one problem worth about 30, and then 15 on the next two, or yeah, something like that. It doesn't matter. It's all relative. I mean, if I give you a test that's worth 78 points, it doesn't matter. Score is based on what you get out of 78, so they could all be worth 1 point, really. All right, but anyway, but that makes it harder to grade. It's either all or nothing, and I hate that. Okay, but anyway, so chapter 8 is going to be one question. Now, this would be a bowling ball rolling. So look up. I'll give you the I for a rolling sphere, for a solid sphere that's rolling about its center of axis. And here's you're going to want to know, I mean, certain things will be given to you, like how fast it's rolling, or what it's, if you know its angular velocity, if it's going at a constant angular velocity without slipping, can you figure out its tangential velocity, its VT? What? Yeah, it gives you the radius. You got the radius, you got the mass of the ball. Why would you need the mass of the ball? Maybe there might be a kinetic energy question, too. Find the total kinetic energy. Total kinetic energy, not just the linear. So don't forget, you're going to have 1/2 mv squared, which we know. Now, what v do we use? What v do we use there? Its center of mass. The velocity of its center of mass. But they might ask you some silly question like this. What's his v up here if he's rolling this way? What's his v up there if he's rolling without slipping? Now, let's say, just for argument's sake, his v down here is 3.0 meters per second. What's his v at the top? The very, very top. Go look at your translational rolling thing. Hal's dying to answer, but he's not going to. He'll probably tell Molly what the answer is, but that's okay. It's 2 times. 2 times. Right? What's its velocity right here at the bottom, right where it's in contact with the road or with the bowling alley? For the split second, right when it's at the bottom. 0, exactly. It's 2v up at the top. All right. Now then, okay. We've already talked about one of the questions that's going to be on the thing, and I might just ask you what the buoyant force is. You know, if I said, hey, you want to submerge this entire beach, what if I told you wanted to submerge an entire beach ball? How much force would you have to apply? You can figure that. A lot, yes. It would be a lot. But you would have to, in other words, whatever the volume of the beach ball is times water times G would be how much, or if you're going to submerge half of it, how much force do you need? That kind of thing. Okay? And then the other question is going to be, we're going to mix some things up. You're going to have to know how to find the mass of something if you're given its density. Okay? Or mainly, let's say we've got something hanging from a very, very thin copper rod. Okay? And it might be a big piece of gold in a sphere. Okay? And it's got a certain amount of tension. You got to be able to figure out what maybe the radius of that thing is from, or it might be a cube. If you're given the tension, you should be able to figure out certain geometrical things if you're told it's a cube or if you're told it's a cylinder and you're given some other things, because rho v equals m, right? And t equals mg. And I was looking at me like, what are you talking about? Here, let me draw it. Expect something like this. I've got a copper rope hanging down like this, and I don't know what kind of thing I'm going to get. Let's put a cube here. Let's put a gold cube. Okay? And the row of gold, the density of gold is 19,300 kilograms per meters cubed. It's 19 times heavier than water, roughly. Okay? So, if this is 1,000 kilograms of water, which would be 2.2 pounds, 1 kilogram is that'd be about a ton of water. It'd be about 38 tons of gold this thing would be. So nobody's going to be stealing it or anything, I don't think. But anyway, if you have gold, and I don't know what a side is, but I do know that the tension in this thing is equal to 1,000 newtons. What's X? And if this has a cross-sectional area of, say, 5.0 times 10 to the negative fifth meters squared, how much is it stretching? Those are two. That's a good problem. I thought it up myself. The numbers might change, or the thing might change, but go practice it, you know, using gold, because you know, oh, tension equals mg. Aha, now we're getting somewhere. And then T equals rho v times g. And so rho times x cubed times g equals the tension. So you should be able to, the hardest thing is going to be finding the cubed button on your calculator. Which one way to find the cubed root is to do this, is to take a number, say you've got 1,000, and you take it to the, you hit the to the 1 divided by 3, 1/3 power, that'll give you 10. You know, that kind of thing. That's one way to find the cubed root on the calculator. Okay? And then delta L, you're using that Young's modulus thing for that material. So I got to find a material that we have the Young's modulus. So it would be hanging from copper or aluminum or something like that, or a piece of femur bone. Because no, wouldn't do that. That's kind of ghoulish. But they do have femur bone in the deal. So then if you hung a gold rod from somebody's femur, how far would it stretch? Ugh. That'd be good. That'd be a biology, because that's gooey. That's a good gooey biology question. All right. Any other questions? That I'm so proud that that thing worked. Usually it kind of goes back to the drawing board, but I figured it out now. All right, you can stop filming. cut. That tells